as a model of a neuron. The idea being that in a real biological neuron, we can classify the inputs in two states, firing or not firing, and the output similarly can be firing or not firing. If we encode the firing as 1, the not firing as 0, you've got binary inputs and you've got a binary output, and one obvious connection between the inputs and the outputs is a logic function. We saw from the Browning and Bledsoe method that if we are sampling n points, n pixels on an image, which is a given class of patterns, for example, the letter T, there would be a limited number of states that would occur for the letter T. And in the example I went through, there's the 3 T's. The top row could be 111 or 110, which gives rise to a logic function. And this logic function, for the top row, it would be sigma 67, which as a Boolean equation, calling the variables A, B, and C. 6 would be A, B, and not C, and 7 would be A, B, and C. And a wonderful property we would note in building up this function, we start off with the first pattern. Sample is 111, which would be a decimal 7, A and B and C. But with a logic function, very important this, when we add a different state, 110, which would be A and B and not C, the function becomes A and B and C, or A and B and not C. I know it will minimize, but don't worry about minimization right now. The important thing is we do not lose the response of the first interval. So the training builds, unlike the analog neuron, where we're changing a hyperplane and we can introduce errors. Errors never occur once the pattern has been trained. Right. Moving on. We can implement the logic functions in random access memories. That's level 1 digital logic design. And for 3 input, we would have an 8-bit memory. And the key thing is the interval becomes the address to the memory, and that interval value is not stored. What we store in the case of A, B, and C would be a 1, a single bit set to 1, in location addressed by the interval. So we have 8 bits of memory, and that remains 8 bits however many training patterns we put in. What changes is the content of the memory. So there is the system with the 3 training logic functions as memories. And what this creates in pattern space is clusters rather than dividing the universe in hyperplanes. Now, the last lecture, I was interested in parameters of the logical neural network. And we were about to build up a bar detector, vertical bars, and I gave you 3 by 3 pixel images, which by human inspection are obviously vertical bars. This one is a bar in the middle. That gives us that pattern. Now, I gave you 3 patterns last week before I think the technology failed me. But what I want to do is to increase the training set. This was pattern 3. Obviously a vertical bar, middle, left, and right. But I also want this to be an intelligent vertical bar recognizer. And so let's introduce a 4th training pattern, which is 2 bars in the image. Now, looking at that, you would say there's vertical bars in that picture. So that would be pattern 4. And I want to carry on. This is going to be a really good vertical bar detector. I want to train on thicker vertical bars as well. So that will be training pattern 5. And the thicker vertical bar to the right. And that would be training pattern 6. Now, I want you to suspend belief now. I am going to tell you that this is a very thick vertical bar. Now, I know you could say it could be a horizontal bar as well, but for the purposes of what I want to demonstrate, that is a training pattern for a vertical bar. You could train the net to recognize that pattern. And again, suspending belief, I want you to regard this as a vertical bar. Absolutely nothing. The bar is so thin, it's below the pixel resolution, and it appears to be invisible. Now, okay, not a really good representative training setting for vertical bars, but it has special properties, and I want to use those patterns. We could actually put those patterns into a network and train what happens. Now, the first mapping I want to use is row by row mapping. Which means I'm looking at each row at a time. So going through for the first function, F1 is going to be the min-term set. For the first one, we have location 2, 0, 1, 0. For the second training pattern, we have 4. For the third training pattern, we have 1. For the fourth training pattern, we have 5. For the fifth training pattern, we have 6. Then 3. Then 7. Then 0. And that is in its original form, a full equation is a complicated logic function. But what does it simplify to? 3 inputs. Any suggestions? Nothing coming forward. Anybody out there? 1! The function responds to everything. And look at sample 2. It's going to be the same. And look at function 3. It's also going to be the same. So all the 3 functions would be 1. It would respond to 1. And the generalization set, let's call it G, the number of patterns in the generalization, is going to be equal to the universe. It fills up the whole universe. And for 9 pixels, 3 by 3, 1 bit per pixel, it is going to be 2 to the 9 equals 512. It responds to everything. It won't work. Now, this is a point I'm trying to make. Let's change the mapping. Change the mapping to column by column. Mapping. And we'll now develop F1 again, the set of terms. And let's have a look at the training data once more. And I'll change pen color. We're now looking at a column. So the first interval will be the column. That will be the second interval. That will be the third interval. And what states do we have? We have 0, 0, 0. Let's go through it. 0, 0, 0, 1, 1, 1. So it's 0 and 7. 0 we've already got. 7 we've got. 7 we've got. 0 we've got. 7 we've got. 0 we've got. So there's only 2 min-terms. And the function is 0, 7. And because it's a symmetrical training set, we're going to get exactly the same functions for F2, the middle column, and F3. So we can say that also equals F2, and that equals F3. Now, so we've got 2 possibilities at each interval sampling state. What is the generalization set for those 3 functions? How many different patterns will it? Now, what's that? A, B? Yes, that's the equation. Now, how many patterns will give a response to F1, F2, and F3? We will have a choice of intervals on the first column, 0 or 7. So it's 2 possibilities in the first column, 2 possibilities in the second column, 2 possibilities in the third column. The generalization set is 2 to the 3. 2 by 2 by 2. 8. Well done. And again, it is useless because it will only recognize the training set. Let's call it T, the set T. 8 patterns it recognizes, 8 patterns in the training set. Whoops. There they are. It will only recognize those 3. Right, so that is also useless, but the important point is, and the point I want you to take on board, is that by changing the mapping, we have gone from recognizing everything, which is no good, to recognizing just the training set, which is better than nothing, but it's just a memory action. There's no generalization, there's no intelligence there. So going back to the set diagram, if those were the 3 training patterns, if I was using the row by row mapping for this particular training set, the generalization set would be the whole universe. If I was using a column by column mapping, the training set and the generalization set, this one here, would be identical. So neither of them is practical for this particular rather silly problem. But what we can do is use a random mapping. And let's just take F1. First of all, let's define the mapping. Let's draw the input space. And let's have the first connection there, the second connection there, and the third connection there. So the first function is going to look at pixel 1, this pixel here, this pixel here, and this pixel here. It's not a column, it's not a row, it's a mixture of both. And that would be F1. Now let's find, oh, come on, don't lock up. Bit slow this morning. F1. Right, we're looking at the top middle, the middle left, and the bottom left. Let's see what states we get from the training set. We're looking at change the color. We're looking at 1, 2, and 3. So it is going to be 1, 0, 0. Let's list the states down here. F1 equals sigma. 1, 0, 0 is 4. 0, 1, 1 is 3. 0, 0, 0 is 0. 0, 1, 1 is 3. We've already got it. Don't need to include it again. 1, 1, 1 is 7. 1, 0, 0 is 4. We've got it. 1, 1, 1 is 7. We've got it. 0, 0, 0 is 0. We have 4 allowable states with that mapping. So if we were to assume it was going to be 0, 1, 4, 7. Was that correct? Let's go back. Is that what I had?
It's 0347.
0347, thanks. Oh. Oh, no, come back. Okay, so we've got 4 terms. 4 possibilities for the first function. Now let's assume F2 and F3 also have 4 states. Then the generalization set for this mapping, G, is going to be 4 possibilities for F1 times 4 possibilities for F2 times 4 possibilities for F3. 4 4s are 16, 64. So with that mapping, the training set of 8 would generalize to a generalization set of 64. It would recognize 64 patterns, and the 512 minus 64 be not recognized. So it is discriminating and it is generalizing. And this shows you that the mapping has quite a significant influence on the behavior. And maybe there's some biological coincidence there. We all have different mappings in our brains. No two brains are the same. Some mappings are good, some mappings are less good. That might be a key to the way we interpret information. Now, how many mappings? Well, for a 3 by 3 pixels, we have 9 pixels. There will be the choices we have for the first sample is 9. It could be this pixel, 1, 2, 3, 4, 5, 6, 7. I could select any of the 9 pixels. The choice for the second pixel to drive the first interval, 8 left, 9 times 8. And for the third one, 7. That's the number of possibilities for the first interval. The second interval, we have a choice of 6 by 5 by 4. And for the last one, 3 times 2, and there's 1 pixel left over. And that, folks, come on, don't freeze on me. Got to slow down. This whiteboard is a way of slowing my lecturing speed down. I'm sure you'll appreciate that. That, of course, equals 9 factorial. And if you've got your calculators, 9 factorial, well done, Demetrius. 9 factorial, what is it as a real number? It is, I think, 362,880 different mappings. Now, it's not quite that number because we can shuffle the mappings around in the function and they will still lead to the same number of states. But that is a huge, impressive number, the number of ways of connecting a 3 by 3 picture to a network of 3 input logic functions. And some are going to be useless, some are going to be much better. And what you will get is a distribution of performances, which will be something like that. Very few will be good, the majority will be average, and some will be absolutely useless. So this is performance distribution. Now, that gives us a possibility to optimize these networks. Try a mapping, find out which are the useful functions which are discriminating, keep them. If a function is not discriminating, throw it away and reconnect it. So optimization is possible. And that is an interesting contrast with the analog neuron using the vector model. It is always fully connected. You have no choice. Every element of the input vector, which could be a pattern, has its own weight and it's always fully connected. Right, so that's the mapping which changes the behavior. The next thing I want to look at for optimizing these networks, going back to our block diagram if I can find it. Oh, come on. Oops. That's a Browning and Bledsoe. Oh, awkward thing to use this. Yes, there we are. The next parameter to optimize is the threshold. So we've looked at the mapping. We're now going to look at the output threshold. Output threshold. Now, the first threshold I want to look at for this very simple example is t equals 3. 3 functions, each function has to respond for the input pattern to be recognized. And this is often referred to as AND generalization. Why is it called AND generalization? Because you have 3 functions coming outputting f1, f2, and f3. We require each of them to be 1 to get a threshold of 3 out of 3. It would be exactly the same as replacing the summer and the threshold with an AND gate. Because if we had an AND gate replacing the summer and its threshold, the AND gate will only respond when all the inputs are 1. It's equivalent of setting a threshold of 3, or in the bigger case, a threshold equal to the total number of functions. Right, the equation for the G AND set, the size of the G AND set, let's call it G AND, is equal to the summation. Let's have a counter I equals 1 to n, which is the number of pixels divided by the n-tuple size. So in our case, n is 9 and little n is 3. So 9 over 3 is 3, the total number of functions. So, what are we summing? We are summing a parameter called ki, where ki is the number of bits set in the memory which is also equal to the number of states in the Browning and Bledsoe model. Okay, let's take another training set. Let's go back to our T recognizer. There's one T, there is another T, and there is the third training pattern T. sloping top. Okay, and let's have a row by row mapping just so we can follow it easily. Okay, this Ki now, the number of bits set in the memory, also the number of states on the interval during training. We're looking at the top row. We have F equals 7, summation 7. Got it already, and 6. Oh. So F1 would be 7 and 6. Looking at the middle row, F2 is the summation. State 2 we've already got, state 3 a new state. So it'll be 2 and 3. And for F3, 0, 1, 0, 2, 0, 0, 0, 0. So function F3 is going to be 0 and 2. Right. That means K1, the number of bits set in the first function, or the number of terms in the logic function, or the number of states on the interval, they are all the same, is going to be equal to 2. 1, 2, 6, 7, 1, 1, 0, 1, 1, 1. It's all the same. K2 is going to be 2 and 3, or 0, 1, 0, and 0, 1, 1. And that is going to be 2. And K3, number of bits set in the third function, number of terms, number of interval states, is also 2. So our generalization set, come on, move up. Don't mess me about. Yes, whoops, steady. Right, so our generalization set for G and, remind you, it is a summation n I equals 1 to the number of pixels divided by the interval size, Ki, and it is going to be 2 times 2 times 2 equals 8. So this training set here, 3 training patterns, n equals 3, capital N equals 9, the number of pixels, and threshold, or equivalent, is the numerical value is 3 out of 3 for this particular simple example. It will recognize 8 patterns. So we now have a problem drawing the universe. We have got a training set T, which equals 3. We have a generalization set GT, which we now know is 8. And of course, what we still don't know is the true data set, which is DT, which is the thing we want to recognize. We know we can modify the size of GT by changing the mapping. So that's a possibility of changing a mapping to map DT, but we're operating on the threshold. Let's see what we can do with a different threshold. Any questions at that point? Yes, John, a quick question. Okay, George, what is it?
Hello, can you hear me?
Yes.
Why is it 8? Shouldn't be 6. Like,
no.
It's a sum, right?
No, it's a multiply. It's a combination.
Oh, okay.
Okay.
Got it. Thank you.
Everybody else okay? Right. Let's go to the other extreme with the same training set. And this is OR generalization. Why is it called OR generalization? It's equivalent to the threshold t equals 1, which means that the network will respond if we have at least one function responding. And it's equivalent of taking the summer and the threshold out of the general model and replacing it with a big OR gate, hence it's called OR generalization. Now, the equation for OR generalization, we have a bit of a problem with OR because the response is not dependent on a unique pattern of values on the output of the functions. With AND, all the functions have to be 1. With OR, all the functions do not have to be 1, but one function, at least one function, must be 1. Now, we could work out all the combinations, but there is an easy way of calculating OR. GOR. The universe minus the inverse of GOR. Now, the universe we can calculate. For 9 pixels, it's 2 to the 9, it's 512 patterns. Now, this not GOR, the inverse of GOR, are the number of patterns that the functions do not respond to. All the functions must give a naught for not GOR. And that is a unique set of values on the outputs of the functions. All have to be naught. So to calculate not GOR is going to be equal to the summation I equals 1 to n over little n. Now, before we had ki, which were the functions that gave f equals 1 for each individual function. If I calculate 2 to the n, little n being the n-tuple size, 3 in our case, there are 8 possible patterns we can get from a binary 3-tuple. If I subtract from that the ki's, which are the number of terms that will give the output 1, what I'm left with is the number of inputs to each function that will give an output 0. And so if I now go back to the previous training set, come on, slide down for me. Right. There we are. These were the functions which were giving f equals 1. There are 2 of them. The total number of inputs to a input values to a 3-input function is 2 to the n, which is 8. If 2 of these functions give f equals 1, 8 minus 2, i.e. 6, must give f equals 0. So if k1, k2, and k3 are all 3 2, then this term for f1 is going to be 8 minus, it's not equal, let's get rid of that. 8 minus 2, 8 minus 2, and that is going to be 6. The same is true for f2, because we had 2 terms in f2 in the previous example, f2 equal 1, and we have 2 terms for f3. So that also equals 6 for those. So this term here, 2 to the n minus ki, for ki equals 1, it's going to be 8 minus 2, 6. Made a mistake. Made a mistake. Yes, thank you, George. You were right. Yes. Yes, indeed. If that was on a black whiteboard in real time, I would have spotted that. Get rid of it. Oh, rubber. Product, not summation. Sorry, I confused you. Product, not summation. Come on, rub out. Oh, it's very slow this morning, right? Product series, not summation. Sorry about that, folks. So it is going to be 6 for K1 times 6 for K2, because K2 is 2 also, times 6 for K3. In real examples, they will differ, but because the example is so simple, we've all turned out to be the same with 2 choices in each function. Are we all okay? Right, good. Good stuff. And that, I think, is 6 6s are 36, which is 216. Those are the patterns which are not in the OR generalization set. So the patterns in GOR is going to be the universe. We're back to this equation here. U is 2 to the 9, which is 512, minus those not in the generalization set, which is 216. And 512 minus 216 is 296, is it? Much larger generalization set. And of course, it's overgeneralizing with that low level. In practice, one would never use t equals 1, because if I go back to the training set, 296 patterns. Come on, move down. Right. Gently does it. Oh, for a whiteboard in the classroom. Now stop there, stop there, stop there, stop. Right, if my threshold was 1 out of 3, I could have 0, 0, 0 on the top row. It wouldn't respond because it's not allowable state. F1 would be 0. I could have 0, 1, 0 on the middle row. It would respond. And I could have 0, 0, 1. Let's try and get that slightly brighter if I can. Oh, come on. That character, that input pattern would give a response of 1. It would pass the OR generalization threshold, and it would be classified as a T. And clearly it is not classified. It's not in real life perceived to be a T. Why does it respond with 1? F1 will be 0. Yes. F2 will be 1. And F3 will be 0. So in practice, neither AND nor OR are used. We will have a threshold. This is case, third case. Not. Let's rub that out. Let's take a threshold. In this case, the case is so simple. We've only got 3 outputs values. It can be 3, it can be 2, it can be 1, it can be 0. Now for threshold values. Now for t equals 2, then the response of the summer of summation in the model is going to be 2 or 3. If it's 1, it's below the threshold of 2 and no response. So to calculate with a threshold of t equals 2, possibilities. F1, the first function, equals 1. F2 equals 1. F3 equals 0. Response, let's call it R, equals 2. The other possibility, F1 equals 1, F2 equals 0, F3 equals 1, R equals 2. It's equal to the threshold the net fires. Third possibility, F1 equals 0, F2 equals 1, F3 equals 1. And there again, R would be 2. Also, and people forget this, come on, move up. Come back, come back. Oh, don't lock up for me, please. I thought it was going to be okay today. Why are my pens not coming up? Ah, oh, what fun this is. Brunel, your computer system is so slow. Come over slowly. Stop there, you stop there. It's supposed to be an intelligent system. It's failing me. Now stay there. Now, can I get my black pen up? Ah, where have the pens gone? They skimped on the budget, I agree. I got my pen back. Well, also, F1 equals 1, F2 equals 1, and F3 equals 1. There R would be equal to 3, and of course it will exceed the threshold of 2. So, and this latter one, can I get the red one without any trouble? This is AND generalization. which we have already calculated. So, come on, 10 minutes left. Machine, keep working for me, please. Let's now take the number of patterns which will give a response of 1 on F1, 1 on F2, 0 on F3. It is going to be for F1, it is going to be K1, the number of states set in the first memory, or the number of terms or the number of intervals, all the same, times the number of ways of getting a 1 on F2, and that was K2, and the number of ways of getting a 0 on F3, which will be 2 to the n minus K3. And this is going to be 2 by 2 by 6. All with me? So the number of ways of getting that pattern of response is 6. Now for the second function, because the number of terms are the same, we need a 1, 0, 1. It is going to be for F2. It is going to be K1 will be the number of ways of getting a 1 on F1 times 2 to the n minus K2 times K3. And that also is 6 because all the K's are 2. And also for F3, it is also 6. And F3 would be K1 times K2 times 2 to the n minus K3. Right. Those are the number of ways of getting a response of 2 1s and a 0 from the network. So the total will be for 2 out of 3, let's call it 2 out of 3, is going to be 6 times 6 times, oops, mistake. Oh, come on, rub out. Go for the first one. 2 times, come on, 2 times 2 times 6, which is 2 4s, which is equal to 24, plus the number of ways of getting the response 0 1 0 1 0 1, which is going to be 2 times 6 times 2, which is also 24, plus the number of ways of getting 0 1 1 on the 3 functions, which will be 6 times 2 times 2, which is also 24. So the total, come on, move up. And this is a response, the last one. Oh, stop it. The other way, plus 2 times 6 times 2, which will be 1 0 1, plus 6 times 2 times 2, and it's all going to be 24. The total is going to be 70, 24, 48, 72 patterns. Now note, this is for response 2 out of 3. We need response? 3 out of 3, because that will also exceed the 2 out of 3 threshold, and that is and generalization. And G and for this problem we've already calculated was 8. So for the, come on, go up. Move. Oh, steady on. So for this problem, G, T greater than or equal to 2 as the threshold is going to be 72 patterns giving a score of 2 plus 8 giving a score of 3 equals 80. So again, we've got a parameter that changes performance. Let's recap. For and generalization, it was 8. For or generalization, it was 296, I think it was. And for the threshold of 2, it is 80. So by changing that threshold, the generalization set can move from a very tight one, 8 out of the universe, up to 80 for a threshold of 2, and it goes over the top to 296 for a threshold of 3. So there is another parameter that can control the generalization. It's 11:56, so that is a very convenient time to end. Right, folks, this will be the last lecture before the break. I assume most of you are already at home. My advice is do take a rest from study sometime over the holiday, but towards the end, after New Year, start looking at some past papers. You should be able to answer about half the questions on the paper from previous years, because we've covered about half the material yet. I wish you a very happy Christmas and the New Year and all your celebrations. Don't go too mad, but try and enjoy yourself. And I really hope next term we can have some face-to-face, because it's so much more fun. And I don't have to fight this rather slow and awkward system. So good luck and happy Christmas and New Year to everybody. And don't give up. We'll overcome this bad period of university teaching and get back to normal, hopefully, in the new year. All the best. Bye.